So, here's something to think about as you settle in tonight. On a summer day in 1950, a group of physicists were walking to lunch at Los Alamos National Laboratory in New Mexico. This was the place where, just a few years earlier, some of the most brilliant minds in human history had gathered to build the atomic bomb. By 1950, the war was over. The lab had shifted to other work, but the culture of that place, the habit of asking enormous, almost absurdly ambitious questions over sandwiches and coffee, that hadn't changed at all. And on this particular day, the conversation had drifted to flying saucers. Now, that might sound a little silly for a group of world-class physicists, but it wasn't entirely frivolous. There had been a recent spate of UFO reports in the news, and someone had published a cartoon in the New Yorker. A cartoon showing aliens stealing trash cans from the streets of New York City, which was meant to explain a rash of missing public trash cans that had been in the papers. The physicists were laughing about it. They were riffing on the idea, the way smart people do when they're relaxed and just enjoying each other's company. Could aliens really visit Earth? What would it take? How fast would they need to travel? And then the conversation moved on to other things, the way lunch conversations do. But a few minutes later, already seated in the cafeteria, already eating, Enrico Fermi suddenly looked up from his lunch and said, with complete earnestness, "But where is everybody?" And the table went quiet. Because everyone there understood exactly what he meant, and they understood that it was a much deeper question than it sounded. Enrico Fermi. Let's talk about him for a second, because he's not just any physicist asking a casual question. This was a man who had won the Nobel Prize in Physics in 1938. He had built the world's first nuclear reactor in a squash court underneath the University of Chicago's football stadium in 1942. He was famous for what people called Fermi estimation, the ability to make remarkably accurate calculations about complex problems using very little data and a lot of clever reasoning. He once estimated the strength of the Trinity nuclear test blast by dropping scraps of paper and watching how far the shockwave carried them. His estimate was within a factor of 2 of the actual yield, and he did it in seconds, standing in the desert, while everyone else was still staring at the mushroom cloud. So when Fermi asked a question, even a seemingly simple one, people paid attention, because they knew he had already done some math in his head, and the math was bothering him. Where is everybody? What he meant was this: the universe is unimaginably vast. Our galaxy alone, the Milky Way, contains somewhere between 100 billion and 400 billion stars, and the Milky Way is just one galaxy among hundreds of billions of galaxies in the observable universe. Many of those stars are billions of years older than our Sun. If even a tiny fraction of them have planets, and even a tiny fraction of those planets developed life, and even a tiny fraction of that life became intelligent and technological, then the universe should be absolutely teeming with civilizations. Some of them should be millions or even billions of years more advanced than us. They should have had more than enough time to develop interstellar travel, to send out probes, to colonize the galaxy, to do something so conspicuous that we couldn't possibly miss it. And yet, as far as we can tell, the universe is silent. We see no signs, no signals, no megastructures, no visitors, nothing. That's the paradox. And it's named after him, the Fermi Paradox, even though the question itself is older than that lunch conversation, and the full implications took decades to unfold. But his name stuck because of how perfectly he crystallized it. Not as an abstract philosophical puzzle, but as a genuine scientific problem. A problem with numbers behind it. Numbers that, when you actually work through them, should make you feel a little uneasy. Let's work through some of those numbers together, slowly, because they're worth sitting with. And don't worry, this isn't going to feel like a math class. It's more like a thought experiment. Just let the scale of it wash over you. Start with our galaxy. The Milky Way is about 100,000 light years across. A light year is the distance light travels. In 1 year, roughly 5.88 trillion miles. So our galaxy alone is almost 600 quadrillion miles wide. That's a number so large it doesn't really mean anything to the human brain, which is fine. The point isn't to grasp the number. The point is to understand that there is an extraordinary amount of space out there, and an extraordinary number of stars within it. Now, our sun is about 4.6 billion years old, but the Milky Way itself is about 13 billion years old. That means there are stars in our galaxy that formed 8 or 9 billion years before our sun even existed. Planets around those stars could have had life developing on them for billions of years before the Earth was even a cloud of dust. Think about what that means. Human civilization, everything from the first cities in Mesopotamia to the phone in your pocket, spans maybe 10,000 years. Technological civilization, the kind that uses radio waves and builds rockets, is barely 150 years old. Now imagine a civilization that had a 5 billion year head start on us. Even if their technological progress was absurdly slow compared to ours, the things they could accomplish in that span of time are almost incomprehensible. And here's the thing about colonizing a galaxy. It doesn't actually require faster than light travel. You don't need warp drives or wormholes or any of the exotic physics from science fiction. You just need ships that can travel at a fraction of the speed of light, say 1% or even 1/10 of 1%, and a willingness to be patient. At 1% of the speed of light, you could cross the entire Milky Way in about 10 million years. That sounds like a long time, and it is, by human standards. But compared to the age of the galaxy, 10 million years is nothing. It's a rounding error. It's less than 1/10 of 1% of the galaxy's lifespan. If a civilization arose just 1 billion years before us, and statistically, many should have, they would have had more than enough time to colonize every habitable star system in the galaxy 100 times over. Even accounting for the time it takes to establish a colony, build new ships, and send them onward to the next star, the math works out. The galaxy should be full, and yet it isn't. Or at least, it doesn't appear to be. That's the paradox. Now, Fermi himself didn't write a paper about this. He asked the question over lunch, did some back-of-the-envelope reasoning with his colleagues, and the conversation moved on. The formalization of the paradox, the careful laying out of the assumptions and the math, came later, most notably from a physicist named Michael Hart in 1975 and an astrophysicist named Frank Tipler in 1980. Hart published a paper called An Explanation for the Absence of Extraterrestrials on Earth, in which he argued that the absence of aliens was, in fact, evidence that we are alone in the galaxy, or very nearly so. Tipler went further and argued that the absence of self-replicating probes, machines that could travel to a star system, mine resources, build copies of themselves, and send those copies onward, was strong evidence that no advanced civilizations exist anywhere in our galaxy. Because the logic was almost inescapable. If such a civilization existed, even once, the probes would have spread everywhere by now. The galaxy would be saturated with them, and we'd know. But before we get deeper into the proposed solutions, and there are dozens of them, each more fascinating and sometimes more unsettling than the last, let's back up and talk about something that happened before Fermi's lunch. Because the question of whether we're alone didn't start in 1950. It's one of the oldest questions humanity has ever asked, and the way people have answered it across the centuries tells you a lot about how our understanding of the universe has evolved. The ancient Greeks debated it. Democritus, the philosopher who first proposed that all matter is made of atoms, around 400 BC, more than 2,000 years before modern atomic theory confirmed he was essentially right. Democritus also argued that the universe must contain countless worlds, some with life, some without. His reasoning was elegant in its simplicity. If atoms are infinite in number, and they combine in every possible way, then worlds like ours must arise again and again throughout the cosmos. His contemporary Epicurus agreed and went further, arguing that it would be absurd to think that Earth was the only world to produce living things, given the infinite material available. But not everyone agreed. Aristotle, whose influence on Western thought is almost impossible to overstate, argued that the Earth was unique, the center of the cosmos, with everything else revolving around it. In Aristotle's model, there was no room for other worlds, because there was only one natural center, one set of concentric spheres, one arrangement. And for nearly 2,000 years, Aristotle's view dominated. The medieval Christian Church adopted and reinforced it, placing Earth and humanity at the center of God's creation. The idea of other inhabited worlds was, at various times, considered heretical. And then Copernicus changed everything. In 1543, Nicholas Copernicus published his model of the solar system with the sun at the center, not the Earth. It took decades for the idea to gain acceptance. Galileo was famously persecuted for defending it. But once it took hold, the philosophical implications were enormous. If Earth isn't the center of the universe, if it's just another planet orbiting just another star, then what makes it special? Why should it be the only place with life? Giordano Bruno, an Italian friar and philosopher, took this idea and ran with it. In the 1580s, he argued that the stars were distant suns, each potentially with their own planets, each potentially harboring life. He envisioned an infinite universe filled with countless inhabited worlds. The Catholic Inquisition burned him at the stake in 1600, though to be fair, his cosmological views were only part of what got him in trouble. He had a talent for irritating powerful people on multiple fronts, but his vision of a universe teeming with life turned out to be remarkably prescient, at least in its broad strokes. By the 18th and 19th centuries, the idea of extraterrestrial life was almost mainstream among educated Europeans. William Herschel, the astronomer who discovered Uranus in 1781, believed that every planet in the solar system was inhabited, including the sun, which he thought had a cool, solid surface beneath its fiery atmosphere. That turned out to be spectacularly wrong, but the impulse behind it, the conviction that life must be everywhere, was widely shared. Percival Lowell, the American astronomer, became famous in the late 1800s for his detailed maps of canals on Mars, which he believed were irrigation channels built by an intelligent civilization struggling to survive on a drying world. He built an entire observatory in Flagstaff, Arizona, largely to study Mars, and he wrote popular books that captured the public imagination. The canals turned out to be optical illusions, tricks of the eye when peering through early telescopes at a blurry, distant surface. But Lowell's work helped cement the idea of Martians in popular culture. So by the time Fermi asked his question in 1950, Humanity had spent centuries assuming, hoping, or arguing that life must exist elsewhere. What made the mid-20th century different was that, for the first time, we had the tools to start actually looking. Radio astronomy was maturing. We understood the electromagnetic spectrum well enough to know what kind of signals an alien civilization might produce. And we were beginning to develop a real, quantitative framework for thinking about the probability of extraterrestrial intelligence. That framework arrived in 1961, when a young astronomer named Frank Drake stood in front of a small group of scientists at the Green Bank Observatory in West Virginia and wrote an equation on a blackboard. The equation wasn't meant to give a definitive answer. It was meant to organize the question, to break the enormous, overwhelming problem of "are we alone?" into smaller, more manageable pieces that could each be estimated and debated separately. And it worked. It worked so well that the Drake equation, as it came to be known, has been the starting point for almost every serious discussion of extraterrestrial intelligence for more than 60 years. Drake had actually already conducted the first modern search for extraterrestrial signals the year before, in 1960. He called it Project Ozma, named after the princess in L. Frank Baum's Oz books, a ruler of a land far away, difficult to reach, and populated by strange and exotic beings. Using an 85-foot radio telescope, he pointed it at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for artificial radio signals at a frequency of 1,420 megahertz, the emission frequency of neutral hydrogen, which Drake and others reasoned would be a natural choice for any civilization trying to communicate, since it's the most common element in the universe, and any technologically capable species would know about it. He listened for about 2 months and heard nothing conclusive, though at one point there was a brief, exciting false alarm that turned out to be a high-altitude aircraft. But Project Ozma wasn't really about finding a signal on the first try. It was about proving the concept, showing that the search could be done, that it was real science, not science fiction. And the meeting at Green Bank the following year, where Drake presented his equation, was about rallying a small but passionate community of scientists around the idea that this search was worth pursuing seriously, systematically, over the long term. The equation itself is deceptively simple. It estimates the number of detectable civilizations in our galaxy by multiplying together a chain of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that could support life, the fraction where life actually develops, the fraction where life becomes intelligent, the fraction that develops technology we could detect, and finally, the average length of time such civilizations remain detectable. Multiply all those terms together, and you get N, the number of civilizations in the Milky Way we might be able to communicate with right now. And here's where it gets really interesting, because when Drake and his colleagues first plugged in their best guesses for each of those factors back in 1961, they came up with a number for N that was somewhere around 10,000. 10,000 civilizations in our galaxy alone, right now, that we could potentially detect or communicate with. And in the decades since, as our estimates for some of those factors have gotten better, we now know, for instance, that planets are far more common than anyone in 1961 imagined. Some of those revised estimates push N even higher. Which brings us right back to Fermi's question, doesn't it? If the math says there should be thousands or even millions of civilizations out there, and if some of them should be millions of years ahead of us, then the silence becomes genuinely strange. It's not just a philosophical curiosity. It's a scientific problem that demands an explanation. And over the past several decades, some of the most creative minds in science have proposed explanations that range from the comforting to the deeply, quietly terrifying. Some of those explanations say the problem is with our assumptions, that we're overestimating how common life is, or how often it becomes intelligent. Others say the problem is with us, that we're looking in the wrong way, or that we're too primitive to recognize what's right in front of us. And some say the problem is with the universe itself, that there's something out there, some barrier, some filter, that prevents civilizations from reaching the point where they'd be visible to us. And the nature of that filter, whether it's behind us or ahead of us, changes everything about how you should think about humanity's future. So, let's sit with that idea for a while, because it really is one of the most profound concepts to come out of the whole Fermi Paradox conversation, and it deserves some careful unpacking. The term great filter was coined by an economist, actually, not an astronomer or a physicist. Robin Hanson, who was at George Mason University, wrote a paper in 1996 called "The Great Filter? Are We Almost Past It?" And what Hanson did was beautifully simple. He laid out the steps that would need to happen for a dead, lifeless planet to eventually produce a civilization capable of colonizing the galaxy. And then he said, look, somewhere along this chain of steps, there has to be at least one step that is extraordinarily unlikely, extraordinarily difficult, because if every step were reasonably easy, the galaxy would already be teeming with visible civilizations. The fact that it isn't, the fact that we see this great silence, means there's a filter somewhere, a bottleneck, a wall that almost nobody gets past. And here's why the location of that filter matters so much. If the great filter is behind us, if it's something we've already passed through, then that's actually good news. It means we're rare, maybe astonishingly rare, but we've already beaten the odds. We're through the hard part. The road ahead might be open. But if the great filter is ahead of us, if it's something that civilizations like ours haven't reached yet, something that lies between where we are now and where a galaxy-colonizing civilization would be, then that's the terrifying scenario, because it means that civilizations regularly get to roughly our stage of development, and then something happens. Something stops them. Every time. So let's walk through the candidates for where that filter might be, starting from the very beginning, from the earliest steps. And I want you to think of this like a staircase. Each step represents a transition that had to happen for us to get here, and any one of them could be the hard one, the one that almost never happens elsewhere. The first step is the most basic one. You need a planet in the right kind of environment, what astrobiologists sometimes call the habitable zone, that Goldilocks region around a star where liquid water can exist on the surface, not too hot, not too cold. Now, when Drake was putting together his equation in 1961, nobody knew how common planets were. We literally had 0 confirmed exoplanets. The first one wasn't discovered until 1992, and the first one orbiting a sun-like star wasn't confirmed until 1995, when Michel Mayor and Didier Queloz found 51 Pegasi b. Since then, missions like Kepler, launched in 2009, have completely transformed our understanding. Kepler alone identified over 2,600 confirmed exoplanets, and the data suggests that there are more planets than stars in our galaxy. More planets than stars. That's remarkable. And a significant fraction of those are rocky, Earth-sized planets in the habitable zones of their stars. So this first step, getting a suitable planet, doesn't seem to be the filter. Planets are everywhere. The second step is the origin of life itself. And this is where things get genuinely mysterious, because we still don't understand how life began on Earth. We know it happened relatively quickly in geological terms. The Earth is about 4.5 billion years old, and the earliest evidence of life dates back to at least 3.5 billion years ago, possibly as far back as 3.8 or even 4 billion years. That's striking. It means life appeared almost as soon as conditions allowed it to, which suggests that maybe the origin of life isn't that hard. Maybe given the right chemistry and the right conditions, life pops up readily. But here's the thing. We have a sample size of exactly one. We have one planet where we know life arose, and we're standing on it. It's very difficult to draw statistical conclusions from a single data point. For all we know, what happened on Earth was a 1 in a trillion fluke, and we just happen to be here to wonder about it because, well, if it hadn't happened, we wouldn't be. There's a concept in philosophy called the anthropic bias, or sometimes the observation selection effect, and it's really important to keep in mind throughout this whole discussion. Basically, no matter how unlikely our existence is, we can only ever find ourselves in a situation where we exist. So the fact that we're here doesn't actually tell us how likely our existence was. It's like if you won a lottery with 1,000,000,000 to 1 odds. From your perspective, it feels like it was inevitable because you're the one holding the ticket. But that doesn't mean the odds were good. It just means someone had to win, and it happened to be you. So the origin of life, abiogenesis, as scientists call it, remains a serious candidate for the Great Filter. Maybe the jump from complex chemistry to the first self-replicating molecule is just stupendously improbable. We've made progress in understanding it. The famous Miller-Urey experiment in 1953 showed that amino acids, the building blocks of proteins, could form spontaneously from simple gases when you add energy. They used electrical sparks to simulate lightning in a flask of water, methane, ammonia, and hydrogen. And since then, researchers have found amino acids in meteorites, in interstellar dust clouds, all over the place. The raw ingredients seem to be common. But going from amino acids to a functioning, self-replicating cell is an enormous leap, and nobody has managed to replicate that in a laboratory. Not yet. There's a huge gap between having building blocks and having a building. Now let's say life does get started. The next step on our staircase is the jump from simple, single-celled life to complex, multicellular life. And this is another really interesting candidate for the filter, because on Earth, this transition took an incredibly long time. Simple prokaryotic life, bacteria and archaea, appeared within the first billion years of Earth's history. But complex eukaryotic cells, the kind with a nucleus and internal organelles, didn't show up until roughly 2 billion years ago. And multicellular life didn't really get going until maybe 600 or 700 million years ago. So for roughly 3 billion years, life on Earth was nothing but single-celled organisms. 3 billion years. That's an almost incomprehensible stretch of time. If Earth's history were compressed into a single calendar year, complex multicellular life wouldn't appear until mid-November. Everything before that, January through October, is just microbes. And here's what's really fascinating about that transition to complex cells. It appears to have happened through an event called endosymbiosis, and this is one of the most beautiful ideas in all of biology. The theory, championed by Lynn Margulis starting in the late 1960s, and she faced enormous resistance, by the way. Her paper was rejected by about 15 journals before it was finally published in 1967. The theory says that our complex eukaryotic cells arose when one simple cell engulfed another, and instead of digesting it, the two formed a partnership. the engulfed cell became the mitochondrion, the powerhouse of the cell, the organelle that generates energy through aerobic respiration. And this partnership was so successful, so transformative, that every complex cell on Earth today, every cell in your body, every cell in every animal and plant and fungus contains descendants of that original engulfed bacterium. But here's the kicker. As far as we can tell, this only happened once. In 4 billion years of life on Earth, the transition from simple prokaryotic cells to complex eukaryotic cells appears to have occurred exactly one time. Every eukaryote on the planet traces back to that single event, which suggests it might be extraordinarily unlikely. Nick Lane, a biochemist at University College London, has written extensively about this, arguing that the energy constraints on simple cells make it almost impossible for them to evolve complexity without something like mitochondria, and that acquiring mitochondria through endosymbiosis is such an improbable event that it might almost never happen. If he's right, then the galaxy could be absolutely teeming with bacterial life, simple, single-celled organisms on billions of planets. But complex life might be vanishingly rare. Bacteria everywhere, but nobody home to build radio telescopes. And even after you get complex cells, you still need to get to multicellular organisms, and then to intelligence, and then to technology. Each of those is another step on the staircase, another potential filter. Think about intelligence for a moment. Life has existed on Earth for nearly 4 billion years. Complex multicellular life has been around for over 500 million years. In that time, evolution has produced an extraordinary diversity of forms. Dinosaurs that ruled for 160 million years, vast forests of ferns and conifers, oceans full of fish and mollusks and crustaceans. But technological intelligence? That's happened exactly once. One species, out of the billions that have ever lived on this planet, has built radios and rockets. Dolphins are smart. Octopuses are remarkably clever. Crows use tools. But none of them are building particle accelerators. Whatever combination of evolutionary pressures produced human-level intelligence, the ability to use language, to think abstractly, to accumulate knowledge across generations, it seems to be either very unlikely or very slow to develop, or both. There's a wonderful thought experiment that the paleontologist Stephen Jay Gould used to talk about. He called it replaying the tape of life. Imagine you could rewind evolution back to some point, say the Cambrian explosion, about 540 million years ago, and let it play forward again with slightly different initial conditions. Would you get intelligence again? Would you get anything like humans? Gould argued probably not. He thought the specific path that led to us was so contingent, so dependent on particular accidents and lucky breaks, that replaying the tape would produce a completely different cast of characters. Others, like Simon Conway Morris at Cambridge, have argued the opposite, that convergent evolution tends to find the same solutions repeatedly, and that something like intelligence might be almost inevitable given enough time. It's a debate that gets right to the heart of whether we should expect the galaxy to be full of thinkers or whether we might genuinely be alone. But let's set aside the question of where the filter is for a moment, because there's a whole other category of explanations for the Fermi Paradox that doesn't rely on a filter at all. These are what you might call the "they're out there but" explanations. And they start from the premise that maybe civilizations do arise, maybe they do become technologically advanced, but for some reason, we just can't see them. And honestly, some of these ideas are just as fascinating as the filter explanations, maybe even more so. because they force us to think about what an advanced civilization would actually look like, how it would behave, what it would want. And those are questions that say as much about us as they do about any hypothetical aliens. So let's start with the simplest version of this idea, which is basically, space is really, really big, and we haven't been looking very hard. This sounds almost too obvious to be worth saying, but when you actually sit with the numbers, it's a surprisingly strong argument. Think about it this way. The Milky Way galaxy is roughly 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars. Our radio signals, the ones we've been broadcasting since the early 20th century, have traveled outward in an expanding sphere for about 100 years. 100 light-years. That sounds like a lot until you realize it's 1/1000th of the diameter of the galaxy. If you imagine the Milky Way as a dinner plate, our radio signals have covered a volume roughly equivalent to a grain of sand sitting on that plate. That's it. That's the extent of our electromagnetic footprint. And it gets worse. Those signals aren't just limited in range, they're limited in power. A television broadcast or a radar pulse might be detectable at interstellar distances if you had an absolutely enormous antenna pointed in exactly the right direction at exactly the right time. But the signal strength drops off with the square of the distance. By the time our broadcasts have traveled even a few light years, they're extraordinarily faint, buried in the background noise of the cosmos. The idea that some distant civilization is picking up episodes of I Love Lucy is a fun image, but the physics doesn't really support it. Now flip that around. What about our ability to detect their signals? SETI, the search for extraterrestrial intelligence, has been running in various forms since Frank Drake pointed that telescope at Tau Ceti and Epsilon Eridani back in 1960. But here's the thing most people don't appreciate about SETI. The search has been incredibly limited. Jill Tarter, who spent decades leading SETI research and was one of the most persistent advocates for the search, had a wonderful analogy for this. She said that comparing all the SETI searches ever conducted to a thorough search of the galaxy is like dipping a glass into the ocean, finding no fish in the glass, and concluding the ocean has no fish. The actual fraction of the sky that's been surveyed, at the right frequencies, with sufficient sensitivity for enough time, is vanishingly small. There's a paper from 2018 by Jason Wright and some colleagues at Penn State that tried to quantify this more rigorously. They defined what they called a cosmic haystack, a multidimensional search space that includes not just which direction you're looking, but what frequency you're listening at, how sensitive your instrument is, what kind of signal you're looking for, whether it's continuous or pulsed, and so on. Their conclusion was that SETI had searched something like a swimming pool's worth of water compared to the Earth's oceans. So when someone says, "We've been searching for decades and found nothing," the honest response is, "We've barely started." And that's a genuinely important point to sit with for a moment, because the absence of evidence argument, the idea that if they were out there, we'd know by now, rests on the assumption that we've actually done a thorough job of looking. We haven't. Not even close. Now that doesn't resolve the paradox entirely, because remember, the strongest versions of the paradox aren't just about detecting signals. They're about the physical colonization of the galaxy. If even one civilization had started expanding outward at even a small fraction of the speed of light, they could have colonized the entire Milky Way in something like 10 to 100 million years. That's a long time by human standards, but it's a blink compared to the age of the galaxy. So the "we haven't looked hard enough" argument works better for signals than it does for the broader question of why nobody seems to have shown up. But this leads us naturally to another category of explanation, and it's one that gets really interesting really quickly. What if advanced civilizations don't expand? What if the assumption that a sufficiently advanced species would inevitably colonize the galaxy is just wrong? This is sometimes called the sustainability argument, or the self-limitation hypothesis, and it takes many forms. The basic idea is that maybe civilizations reach a certain level of technological capability and then settle down. They find an equilibrium. They stop expanding, not because they can't, but because they choose not to, or because the economics don't make sense, or because their values evolve in ways that make endless expansion seem pointless or even harmful. Think about our own history for a second. Humans have had the technological ability to colonize the ocean floor for decades. We could build permanent underwater habitats. We have the engineering knowledge. But we haven't done it in any meaningful way because it's incredibly expensive, there's not much incentive, and frankly, most people don't want to live on the ocean floor. The same might be true of interstellar colonization. Maybe it's technically possible but practically unappealing. Maybe civilizations that survive long enough to develop the technology also develop the wisdom, or the laziness, or the contentment to stay home. There's a related idea that the science fiction writer Carl Schroeder has explored, which he calls the rewilding hypothesis. The notion is that truly advanced civilizations might become so efficient, so good at managing their resources and their energy use, that they become essentially invisible. They don't build Dyson spheres or megastructures. They don't blast radio signals across the cosmos. They live quietly, in balance with their environments, using only what they need. From the outside, their star systems might look completely natural. You wouldn't know anyone was home. And here's what's really clever about that idea. It flips our assumptions about what advancement looks like. We tend to imagine that a more advanced civilization would be louder, bigger, more visible. More energy consumption, more megastructures, more everything. But what if the opposite is true? What if the trajectory of a truly successful civilization is toward less waste, less noise, less disruption? We already see hints of this in our own technology. Modern computer chips are vastly more powerful than their predecessors, but use less energy per computation. LED lights produce more light with less heat. The trend, in many domains, is toward efficiency, toward doing more with less. Extrapolate that trend across millions of years, and you might end up with civilizations that are extraordinarily capable, but essentially undetectable. Now, there's a counter-argument to all of this, and it's a strong one. It only takes one. Even if 99% of civilizations choose to stay home and live quietly, if even 1%, even one single civilization, decides to expand, that should be enough to fill the galaxy. The sustainability argument requires that every single civilization, without exception, makes the same choice. And that seems like a lot to ask, especially across billions of years and potentially millions of independent civilizations. This is sometimes called the non-exclusivity problem, and it's one of the toughest challenges for any explanation that relies on civilizations choosing a particular behavior. Unless, of course, there's something we're missing about what happens to civilizations as they advance. And this brings us to one of the most haunting explanations for the Fermi Paradox, one that connects back to the great filter idea, but plants the filter firmly in our future rather than our past. What if civilizations tend to destroy themselves? This is the self-destruction hypothesis, and it's probably the explanation that keeps physicists and philosophers up at night, which is ironic, given that we're supposed to be helping you sleep. But stay with me here, because the logic is worth understanding. The argument goes like this. Any civilization that develops the technology to communicate across interstellar distances or to begin colonizing other star systems will, along the way, inevitably develop technologies that could also destroy it. Nuclear weapons are the obvious example. We developed those before we developed space travel. But you can extend the list. Biological weapons, artificial intelligence that might not share our values, climate change driven by industrial technology, resource depletion. Any technology powerful enough to reshape a planet is also powerful enough to ruin one. And here's the uncomfortable part. We have exactly one example of a technological civilization, and that civilization, us, came within a hair's breadth of nuclear annihilation on multiple occasions during the Cold War. There's a story about a Soviet naval officer named Vasily Arkhipov that's worth telling here. It was October 1962, the Cuban Missile Crisis. Arkhipov was the flotilla commander aboard a Soviet submarine, the B-59, in the waters near Cuba. The Americans were dropping practice depth charges, signaling depth charges, really, trying to force the submarine to surface. But the crew of the B-59 didn't know they were practice charges. They'd been out of radio contact with Moscow. They didn't know if war had already started. The submarine's captain, Valentin Savitsky, wanted to launch a nuclear torpedo. The political officer on board agreed. On any other Soviet submarine in that flotilla, that would have been enough. 2 senior officers in agreement. But by a quirk of the command structure, Arkhipov, as flotilla commander, had to agree too. And he refused. He insisted they surface and await orders. One man's judgment, in a sweltering submarine with no air conditioning and failing batteries, possibly prevented a nuclear exchange that could have killed hundreds of millions of people. That's how close we came. And that was just one incident. There were others. The 1983 Soviet early warning false alarm, where Stanislav Petrov decided not to report what his instruments were telling him was an incoming American missile strike because his gut told him the system was malfunctioning. He was right. It was a software error caused by sunlight reflecting off high-altitude clouds. But if he'd followed protocol, the Soviet leadership might have launched a retaliatory strike against a first strike that never happened. So when someone suggests that civilizations might routinely destroy themselves before they become spacefaring, it's not an abstract philosophical argument. We have direct evidence that it almost happened to us, multiple times, and we've only had nuclear weapons for about 80 years. The question, then, is whether self-destruction is the rule or the exception. Is it something that most civilizations stumble through and survive, the way we've survived so far? Or is it a genuine bottleneck, a filter, that most civilizations don't make it past? We simply don't know. We can't know from a sample size of 1. But there's a subtler version of the self-destruction argument that doesn't require outright annihilation. Maybe civilizations don't blow themselves up. Maybe they just stall. They hit resource limits. They lose social cohesion. They turn inward. They develop technologies of distraction and comfort so effective that the drive to explore and expand simply evaporates. This is sometimes half-jokingly called the Great Filter is Netflix hypothesis, but there's a serious point underneath it. A civilization that can create perfect virtual realities, that can simulate any experience, that can provide every individual with a customized paradise inside their own mind. Why would that civilization bother with the enormous expense and danger of interstellar travel? Why cross the void between stars when you can create entire universes inside a computer? And this connects to something that the economist Robin Hanson, the same person who formalized the Great Filter concept, has written about regarding the future trajectory of civilizations. He's argued that the internal dynamics of a civilization, its economics, its politics, its cultural evolution, might matter far more than its raw technological capability when it comes to determining whether it expands outward or turns inward. A civilization might have the rockets, but not the will. It might have the physics, but not the funding. It might have the knowledge, but not the institutional consensus to commit to something so vast and so uncertain. And that's a really important distinction, because when we talk about the Fermi Paradox, we often frame it as a question about capability. Can a civilization build starships? Can it survive long enough to reach other stars? But Hanson's point is that capability might not be the bottleneck at all. The bottleneck might be motivation, desire, the collective will of an entire species to do something extraordinarily hard when there are easier, more pleasurable alternatives available. Think about your own life for a second. You have access to more knowledge right now than any human being who lived before about 1995. You could learn orbital mechanics tonight. You could study xenobiology. You could teach yourself to build a radio telescope from surplus electronics. The knowledge is there, freely available. But you're lying in bed listening to someone talk you to sleep, and honestly, that's a perfectly reasonable choice. Multiply that by an entire civilization, and you start to see the shape of the argument. It's not that the civilization can't expand. It's that expanding is hard and uncomfortable and dangerous, and staying home is warm and safe and filled with interesting distractions. And maybe, across the galaxy, that's what happens over and over and over again. Civilizations reach a certain level of comfort and sophistication, and they just settle in. Now, there's a natural objection to this, and it's worth spending a moment on it, because it comes up every time someone proposes a behavioral explanation for the Fermi Paradox. The objection is what we might call the non-uniformity problem, or sometimes the diversity argument. It goes like this. Sure, maybe some civilizations turn inward, maybe even most of them. But all of them, every single one? Across billions of stars and billions of years? It only takes one civilization that bucks the trend, one species that's restless enough or curious enough or expansionist enough to keep pushing outward, and the galaxy should be colonized. That's the power of the original paradox. It doesn't require every civilization to expand. It just requires one. And this is a genuinely strong objection. It's the reason why behavioral explanations on their own have a hard time fully resolving the paradox. You can tell a plausible story about why any individual civilization might choose not to expand, but it's much harder to tell a convincing story about why none of them would. Because civilizations aren't monolithic. Even within a single species, you'd expect variation. You'd expect some groups that want to stay home, and some groups that want to explore. Some cultures that prioritize comfort, and some that prioritize discovery. And across different species, on different worlds, with different evolutionary histories, and different psychologies, the variation should be enormous. The idea that every single spacefaring civilization in the history of the galaxy would independently arrive at the same decision to stay home, it strains credibility. It really does. So where does that leave us? Well, this is where we start moving into a different category of explanations entirely. We've talked about filters, things that prevent civilizations from arising or surviving. We've talked about choice, civilizations that could expand but don't want to. Now, let's talk about a third possibility. one that's become increasingly popular and increasingly sophisticated over the past couple of decades. And that's the idea that they are out there, but we can't detect them. Not because they're hiding, necessarily, but because the universe is structured in a way that makes detection extraordinarily difficult, or because our assumptions about what we should be looking for are wrong. This is sometimes grouped under the umbrella of they exist, but we can't see them, and it contains a whole zoo of sub-hypotheses, some very serious and some pretty wild. Let's start with the serious ones. The most straightforward version is simply an extension of the search argument we touched on earlier. Jill Tarter's ocean analogy, the cosmic haystack. The idea that our search has been so limited, so narrow in frequency and time and sky coverage, that we could easily have missed signals that are out there. But let's push deeper than that now, because there's a more fundamental issue lurking underneath the search argument, and it has to do with what kind of signals we're even looking for. When SETI began in earnest with Frank Drake's Project Ozma in 1960, the assumption was that extraterrestrial civilizations would communicate using narrow-band radio signals. This made sense at the time. Radio was our most powerful communication technology. Radio waves travel at the speed of light. They pass through interstellar dust and gas relatively unimpeded. And a narrow-band signal, one concentrated at a single frequency, would stand out against the natural radio noise of the cosmos like a lighthouse beam against a dark sky. The logic was elegant, and it drove SETI strategy for decades. You point your radio telescope at a star, you scan across frequencies, and you look for a sharp spike, an unmistakably artificial signal rising above the background. But here's the thing. That logic contains a hidden assumption, and the assumption is that other civilizations would choose to broadcast in a way that's easy for us to detect. And why would they? Think about the trajectory of our own communications technology. In the early 20th century, we were broadcasting powerful radio signals into space. AM radio, FM radio, early television. These signals radiated outward in all directions, expanding in a sphere at the speed of light. Right now, there's a shell of our old radio broadcasts about 100 light-years in radius, washing over distant star systems. But that shell is getting weaker as it expands, and more importantly, our technology has changed. We've moved from broadcast to cable, from analog to digital, from omnidirectional antennas to tightly focused satellite beams and fiber optic cables. Our planet is actually getting quieter in radio terms, not louder. A civilization monitoring Earth from a distant star would have found us easier to detect in 1970 than in 2020. We're becoming radio invisible, not because we've gone silent, but because our technology has become more efficient. And this is a pattern you might expect to see everywhere. Early in a civilization's technological development, it's noisy. It broadcasts wastefully in all directions. But as it matures, its communications become more targeted, more efficient, more encrypted, and harder to distinguish from random noise. An advanced civilization's signals might be indistinguishable from the cosmic microwave background as far as our instruments are concerned. We'd be listening for a shout in a world of whispers, and the shout only lasted for a few decades out of a civilization's entire history. This is sometimes called the brief window hypothesis, and it was articulated clearly by the astronomer Seth Shostak, among others. The idea is that there's only a narrow window in a civilization's development, maybe a century or two, during which it's producing the kind of detectable, omnidirectional radio leakage that SETI is designed to find. Before that window, the civilization hasn't invented radio yet. After it, the civilization has moved on to communication methods we can't detect or don't know to look for. And if that window is short, relative to the age of the galaxy, then the chances of two civilizations having their windows overlap, while also being close enough to detect each other, become vanishingly small. But it gets even more interesting than that, because it's not just about radio. Over the past 20 years or so, there's been growing interest in what are called technosignatures, any detectable sign of technology, not just communication signals. And this opens up a much wider range of things to look for. You could look for the spectral signatures of industrial pollution in a planet's atmosphere. You could look for the waste heat of massive engineering projects. You could look for artificial structures that block starlight in unusual patterns. You could look for laser pulses, which can actually be more efficient than radio for point-to-point interstellar communication. And this brings us to one of the most fascinating and controversial episodes in recent Fermi Paradox history, which is the story of Tabby's star. Its official designation is KIC 8462852, but it's named after Tabitha Boyajian, the astronomer at Yale, who first drew attention to its bizarre behavior. In 2015, Boyajian and her colleagues published a paper describing something genuinely strange. This star, observed by the Kepler Space Telescope, was dimming in ways that didn't match any known natural phenomenon. Most exoplanet transits, when a planet passes in front of its star, produce a smooth, symmetrical dip in brightness. A few percent at most. Tabby's star was dimming by up to 22%, in irregular, asymmetric patterns that didn't repeat on any obvious schedule. Now, there are natural explanations: cometary debris, dust clouds, internal stellar variability. And over the following years, additional observations, particularly spectroscopic data showing that the dimming was wavelength dependent, meaning shorter wavelengths were blocked more than longer ones, strongly suggested that fine dust was the culprit, not solid structures. Solid objects would block all wavelengths equally. Dust scatters and absorbs shorter wavelengths preferentially. So the scientific consensus has largely moved toward a natural explanation involving circumstellar dust. But for a brief, thrilling moment, Tabby's star put the concept of megastructures on the front page, because one of the hypotheses floated, not by fringe figures but by serious astronomers like Jason Wright at Penn State, was that the dimming pattern was consistent with what you might expect from a partially constructed Dyson swarm. And a Dyson swarm is one of those ideas that sounds like pure science fiction until you actually think through the physics, and then it starts to seem almost inevitable. The concept goes back to Freeman Dyson, the brilliant British-American physicist who published a short paper in 1960, the same year as Project Ozma, actually, which is a nice coincidence. Dyson's argument was beautifully simple. Any civilization with growing energy needs will eventually exhaust the energy resources of its home planet. The next logical step is to capture more of the energy output of its star. Not a little more, a lot more. A star like our Sun radiates about 3.8 times 10 to the 26th watts of power. Earth intercepts less than a billionth of that. The rest just radiates into empty space. Dyson proposed that an advanced civilization would build a swarm of structures, satellites, habitats, solar collectors, orbiting its star, gradually capturing more and more of that wasted energy. In the theoretical limit, the swarm would completely enclose the star, capturing all of its output. And here's what's clever about Dyson's reasoning. He wasn't just speculating about what aliens might build. He was making a prediction about what we should look for, because a Dyson swarm wouldn't be invisible. It would absorb starlight and re-radiate the energy as infrared radiation, waste heat. So a civilization that had built even a partial Dyson swarm around its star would show up in infrared surveys as an anomalous source. The star would appear dimmer in visible light, but brighter in infrared than you'd expect, and that's something we can actually search for. In fact, several surveys have looked for exactly this. Jason Wright and his collaborators conducted a search using data from the WISE satellite, the Wide Field Infrared Survey Explorer, looking at entire galaxies for signs of anomalous infrared excess that might indicate galaxy-spanning civilizations harvesting energy from millions of stars. The results, published around 2015, found no clear candidates out of roughly 100,000 galaxies surveyed, which is either deeply discouraging or deeply informative, depending on how you look at it. If Kardashev Type 3 civilizations that harness the energy of entire galaxies, existed in any of those 100,000 galaxies, we should have seen them. And we didn't. But absence of evidence at that scale doesn't rule out smaller-scale engineering. A civilization with a partial Dyson swarm around a single star in our own galaxy would be much harder to spot. It might just look like a slightly odd infrared source among billions of stars. And this is where the search stands right now, in that frustrating middle ground where we've ruled out the most dramatic possibilities but haven't yet had the sensitivity to rule out the more modest ones. And this connects to a broader point about the Fermi Paradox that I think is really important and sometimes gets lost in the discussion. The paradox isn't static. It evolves as our observational capabilities improve. Every new telescope, every new survey, every new detection method either deepens the mystery or narrows the space of possible explanations. The Fermi Paradox of 1950 is not the same as the Fermi Paradox of 2024, because we know enormously more now than Fermi did when he asked his question over lunch. We know there are billions of potentially habitable planets. We know that the chemistry of life isn't rare. We know that at least some of the filters we might have worried about, the formation of planets, the availability of organic molecules, probably aren't the answer. And we've started to rule out the most visible forms of galactic engineering. Each of those findings tightens the constraints. Each one makes certain explanations less likely and others more likely. And that's actually exciting, even if it doesn't give us a definitive answer yet, because it means the question is becoming sharper, more focused, more tractable. We're not just philosophizing anymore. We're doing science. Which brings us to another category of explanation that has gained a lot of traction in recent years, and it's one that flips the entire framing of the paradox on its head. What if the reason we don't see evidence of extraterrestrial civilizations is not that they're absent, not that they're hiding, not that they've destroyed themselves, but that we're thinking about this the wrong way? That maybe we're the ones who are confused, not about the universe, but about ourselves, about where we are, about when we are, about what we should expect to see given our actual position in cosmic history. This idea has a name, and it's one of those names that sounds deceptively simple. It's called the zoo hypothesis, or the planetarium hypothesis, or, in its most rigorous modern form, the simulation argument. But before we get to those more exotic versions, let's start with the most grounded and, I think, the most quietly devastating version of this idea. It comes from a concept you might have heard of called the rare earth hypothesis, and it was laid out most thoroughly by Peter Ward and Donald Brownlee in their book published in 2000. Now, we've already talked about some of the filters that might make complex life rare: the eukaryotic transition, the emergence of intelligence. Ward and Brownlee took all of those individual arguments and wove them into something much bigger. Their claim wasn't just that one step is hard. Their claim was that the Earth itself, this particular planet, in this particular solar system, in this particular part of this particular galaxy, is extraordinary in ways we dramatically underestimate. And not just in one way, in dozens of ways, all stacked on top of each other. Think about what you need. You need a planet in the habitable zone, sure, but you also need that zone to be stable over billions of years, which means you need a star that's the right type, not too massive, because massive stars burn out too fast, and not too small, because small red dwarfs tend to be flare stars that would strip away your atmosphere. You need a planet with plate tectonics, because plate tectonics recycle carbon and regulate the greenhouse effect over geological timescales. Without plate tectonics, you get Venus, a runaway greenhouse that bakes the surface at 460 degrees Celsius. You need a large moon, because our moon stabilizes Earth's axial tilt. Without the moon, Earth's tilt would wobble chaotically over millions of years, swinging between extremes that would make stable climates impossible. And our moon is weirdly large relative to Earth. It was probably formed by a Mars-sized body slamming into the early Earth about 4.5 billion years ago. An event so specific and so violent that it might be genuinely rare. You need a magnetic field, generated by a liquid iron core, to shield the atmosphere from solar wind. You need Jupiter, or something like Jupiter, parked in the outer solar system, acting as a gravitational shield, sweeping up comets and asteroids that would otherwise bombard the inner planets so frequently that complex life could never get a foothold. You need your solar system to be in the right part of the galaxy, not too close to the galactic center, where radiation is intense and stellar encounters are frequent, and not too far out, where heavy elements are scarce. The Sun sits in what's sometimes called the galactic habitable zone, and it orbits the galaxy at roughly the same speed as the spiral arms rotate, which means it doesn't pass through those dense, dangerous arms very often. That's called co-rotation, and it might matter enormously. Ward and Brownlee's argument is that when you multiply all of these requirements together, each one maybe not impossibly rare on its own, but each one cutting down the odds, you end up with a number that's vanishingly small. Maybe microbial life is common. Maybe the galaxy is full of pond scum. But complex, multicellular, intelligent life? That might require such a specific and unlikely combination of circumstances that Earth could be one of a handful of places in the entire galaxy where it's happened. Maybe the only one. Now, this hypothesis has its critics, and they make fair points. Some of the requirements Ward and Brownlee list might not be as strict as they claim. Maybe you don't need a large moon. Maybe tidal locking to a red dwarf could provide stability in a different way. Maybe plate tectonics aren't the only mechanism for carbon cycling. The trouble is, we only have one example of a planet with complex life, so we can't really distinguish between requirements that are truly necessary and ones that just happen to be features of our particular case. It's the mother of all sample size of one problems. But here's where this connects to the Fermi Paradox, in a way that I think is really profound. If the rare Earth hypothesis is even partially correct, then the paradox dissolves, not because anything dramatic happened to alien civilizations, not because they're hiding, not because they destroyed themselves, but simply because they were never there. The universe is big and old and magnificent, and it's mostly empty of minds. We're not being ignored. We're not being quarantined. We're just early or rare or both. And that word early brings us to an argument that I find personally fascinating, partly because it's so counterintuitive. It's the idea that we might be among the first technological civilizations in the observable universe, not because we're special, but because of timing. Here's the reasoning. The universe is about 13.8 billion years old. The first generation of stars, population 3 stars, astronomers call them, formed from almost pure hydrogen and helium. They contained essentially no heavy elements, no carbon, no oxygen, no silicon, no iron. You can't build rocky planets out of hydrogen and helium. You certainly can't build biochemistry. Those heavy elements had to be forged in the cores of stars and scattered into space when those stars exploded as supernova. Then the next generation of stars formed from that enriched material, and some of them exploded too, enriching the interstellar medium further. It took several generations of stellar birth and death before there were enough heavy elements floating around to form rocky planets with complex chemistry. The Sun is a relatively late generation star. It formed about 4.6 billion years ago, roughly 9 billion years after the Big Bang. And it took another 4 billion years for intelligent life to evolve on one of its planets. So from the Big Bang to us is about 13.8 billion years. But here's the thing. The conditions necessary for rocky planets and complex chemistry probably weren't widespread in the galaxy until maybe 6 or 7 billion years ago, which means the window during which technological civilizations could have arisen might be much shorter than the age of the universe suggests, maybe only 6 or 7 billion years. And if it takes roughly 4 billion years for a planet to go from formation to technological intelligence, which is what it took here, then the earliest possible civilizations might have arisen only 2 or 3 billion years ago, and we showed up about now. That doesn't make us first, necessarily, but it means we might not be as late to the party as the raw numbers suggest. The universe might look empty not because civilizations have come and gone, but because the whole process of producing civilizations has only recently become possible on a large scale. We might be in the first wave. The 1% of all civilizations that will ever exist. Tom Westby and Christopher Consolis at the University of Nottingham published a paper in 2020 attempting to estimate the number of communicating civilizations in the galaxy using what they called the astrobiological Copernican principle, and under their stronger assumptions, they estimated around 36 active communicating civilizations in the Milky Way right now. 36 in a galaxy of hundreds of billions of stars. And the average distance to the nearest one would be about 17,000 light-years. At that distance, even if they were broadcasting, we'd need enormously more sensitive equipment than we currently have to detect them. And their signals, traveling at the speed of light, would take 17,000 years to reach us. Any conversation would span geological timescales. This connects back to something Jill Tarter said, which we touched on earlier. The idea that we've barely begun to search, but it adds a temporal dimension to the argument. It's not just that we haven't searched enough of space, it's that we might be searching at the wrong time. Or rather, at a time when there simply aren't many signals to find yet. There's a beautiful melancholy to this idea, if you sit with it. The universe isn't hostile. It isn't indifferent in some cold, philosophical sense. It's just young. The story of intelligence in the cosmos might be a story that's barely begun. We might be living in the opening pages. The great civilizations, the ones that will build things we can't even imagine. They might not exist yet. They might be waiting to be born on planets that are still forming right now, around stars that are still collapsing out of molecular clouds. And in that framing, the silence isn't eerie. It's the silence of early morning before the world wakes up. Now, I want to be careful here, because this is the kind of idea that can feel satisfying without necessarily being well supported. The truth is, we don't know how long it takes for intelligence to evolve on a typical habitable planet. We have exactly one data point. Maybe 4 billion years is fast. Maybe it's slow. Maybe on a planet with slightly different conditions, more energy, more chemical diversity, fewer mass extinctions. Intelligence could arise in 1 billion years, in which case civilizations could have been popping up for 5 or 6 billion years already, and we're back to the original paradox. This is what makes the Fermi Paradox so maddening and so wonderful at the same time. Every explanation you reach for has a counterargument. Every solution opens a new question. It's like one of those nested puzzles where each layer reveals another layer underneath. But there's one more category of explanation that we haven't really explored yet, and it's the one that tends to make people the most uncomfortable. It's also the one that some very serious thinkers, not crackpots, not science fiction writers, but philosophers and physicists at major universities, have argued deserves genuine consideration. And it starts with a question that sounds absurd, but turns out to be surprisingly hard to dismiss. What if we're not seeing alien civilizations because what we think of as reality isn't quite what we think it is? What if the nature of our existence is itself part of the answer? This idea comes in several flavors, and the mildest one, the one that requires the least radical rethinking, is something called the zoo hypothesis. It was proposed by John Ball, a radio astronomer at MIT, in a paper published in 1973, and the basic idea is almost embarrassingly simple. Ball suggested that extraterrestrial civilizations might be aware of us but deliberately avoiding contact, the way a wildlife preserve keeps humans away from animals in their natural habitat. Think about that. We set up nature reserves all the time, places where we deliberately choose not to interfere, because we understand that our presence would change the very thing we're trying to observe. We put cameras in the forest instead of walking through it. We watch from helicopters instead of landing. And the whole point is that the animals never know we're there. Ball's argument was that any civilization advanced enough to reach us would also be advanced enough to understand the value of non-interference. They'd recognize that contacting a younger civilization, one still figuring out basic physics, still fighting wars over territory, still burning fossil fuels, would be like walking into a pristine rainforest with a megaphone. You'd contaminate the experiment. You'd alter the natural development of that species in ways you couldn't predict or undo. And so they'd watch, quietly, from a distance. Maybe they'd have rules about it, something like Star Trek's Prime Directive, which is a concept Gene Roddenberry actually explored just a few years before Ball's paper, though Ball was thinking about it from a scientific rather than fictional perspective. Now, the zoo hypothesis has a certain elegance to it. It explains the silence without requiring that civilizations are rare or that they destroy themselves. It doesn't need any particular great filter. It just needs one assumption, that sufficiently advanced civilizations converge on a shared ethic of non-contact, and you can see why that might happen. We've developed that ethic ourselves, at least partially. We have the concept of uncontacted peoples, indigenous groups in the Amazon, on North Sentinel Island, where we've collectively decided, after centuries of disastrous first contacts, that the best thing we can do is leave them alone. So it's not crazy to imagine that a civilization millions of years older than us might reach the same conclusion on a cosmic scale. But here's where the objections start piling up. And they're the same kind of objections we talked about earlier with the self-limitation explanations. The zoo hypothesis requires uniformity. It requires that every single advanced civilization in the galaxy agrees to the same policy. Everyone. Because it only takes one rule breaker, one civilization that says, you know what? I don't care about the cosmic prime directive. I'm going to say hello, and the whole thing falls apart. And when you're talking about potentially thousands or millions of civilizations spread across billions of years, The idea that none of them would ever break ranks starts to feel pretty shaky. It's the non-exclusivity objection again, just wearing a different hat. Ball himself acknowledged this, to his credit. He suggested that maybe there's a single dominant civilization, or a coalition of civilizations, powerful enough to enforce the quarantine. A kind of galactic government that keeps everyone in line. But now you're stacking assumptions on top of assumptions. You need not just advanced civilizations, but a coordinated galactic authority with the ability to monitor and enforce behavior across 100 billion star systems. It's not impossible, but it's a lot to swallow. Still, the zoo hypothesis opened a door. It introduced the idea that the answer to the Fermi Paradox might not be about what's out there, but about what we're allowed to see. And once you walk through that door, things get progressively stranger. The next step down this path is something called the planetarium hypothesis, and it was articulated most clearly by Stephen Baxter in 2001. Baxter is primarily known as a science fiction writer, but this particular idea was presented in a serious academic paper, and it builds on the zoo hypothesis in a way that's genuinely unsettling. Here's the setup. The zoo hypothesis says they're watching us but not interfering. The planetarium hypothesis says something more radical. What if they're not just watching? What if they've actually constructed what we see? What if the universe as we observe it, the empty sky, the silence on all radio frequencies, the apparent absence of anyone else, is a kind of simulation or projection designed specifically to make us think we're alone? Imagine you're an animal in a zoo, but it's not an ordinary zoo. It's so sophisticated that the enclosure looks exactly like the wild. The horizon looks real. The sky looks real. You have no way of knowing you're in an enclosure because every sensory input you receive has been carefully crafted to be indistinguishable from nature. That's the planetarium hypothesis. We think we're looking at the real universe, but we might be looking at a constructed display, a planetarium, in Baxter's metaphor, built by a civilization so far beyond us that we can't detect the seams. Now, you might immediately think, okay, this is just science fiction. This can't be taken seriously. But here's what makes it interesting from a philosophical standpoint. It's actually very difficult to rule out. If the simulation or the projection is good enough, if it's perfect, in fact, then by definition, there's no observation you could make that would reveal it. Every telescope you build, every signal you search for, every experiment you run, all of it happens inside the planetarium. Your data confirms the illusion, because the illusion includes the data. It's an unfalsifiable hypothesis, which means it's not really science in the strict Popperian sense. You can't design an experiment to test it. But unfalsifiable doesn't necessarily mean wrong. It just means we can't prove it one way or the other with the tools we have. And this is where we slide into the deepest, most philosophically treacherous version of this whole line of thinking, the simulation argument. This is the one that gets the most attention, the one that Elon Musk likes to bring up at parties, and the one that was formalized not by a physicist or an engineer, but by a philosopher named Nick Bostrom at Oxford University. Bostrom published his simulation argument in 2003 in a paper called "Are You Living in a Computer Simulation?" And despite the provocative title, the paper is remarkably careful and logically rigorous. It's not an argument that we are living in a simulation. That's a common misunderstanding. It's a trilemma, a logical structure that says one of three things must be true, and we don't know which one. Here's how it works. Bostrom asks you to consider a civilization that has reached what he calls technological maturity, a level of computing power so vast that it could simulate entire worlds, complete with conscious beings who don't know they're simulated. We're not there yet, obviously, but think about the trajectory. In 1970, the most powerful computer in the world could do maybe 100 million calculations per second. Today, the best supercomputers do over a quintillion. That's a billion, and we're still going. If computing power keeps growing, even slowly, for another few centuries or millennia, the idea that you could simulate a world, including the brains of the people in it, starts to look less like fantasy and more like engineering. So Bostrom says, consider 3 possibilities. Number 1, almost all civilizations go extinct or stagnate before they ever reach the level of computing power needed to run these kinds of simulations. Number 2, civilizations that do reach that level almost universally choose not to run ancestor simulations. Maybe they think it's unethical. Maybe they're not interested. Maybe there are laws against it. Or number 3, we are almost certainly living in a simulation right now. And here's the logic. If neither 1 nor 2 is true, if civilizations do reach technological maturity and some of them do run simulations, then the number of simulated worlds would vastly outnumber the one real world. Think about it. One real civilization could run millions, maybe billions of simulated civilizations. Each of those could potentially run their own simulations. The number of simulated conscious beings would overwhelm the number of real ones by an astronomical ratio. And if you're a conscious being, and you don't know whether you're real or simulated, the sheer statistics suggest you're almost certainly simulated. It's like reaching into a bag with 1 red marble and 1 billion blue marbles and asking what color you pulled out. The math says blue. Now, let's be clear about what Bostrom is and isn't claiming. He's not saying we definitely live in a simulation. He's saying that if you reject that conclusion, you have to accept one of the other 2 options. Either civilizations reliably destroy themselves before reaching that computing threshold, or they reliably choose not to simulate. And both of those are themselves strong claims about the nature of intelligent life in the universe. You can't just wave the simulation argument away without committing to a position about the future of all civilizations everywhere. That's what makes it so sticky. And here's where it connects back to the Fermi Paradox in a way that's kind of beautiful, in a dark sort of way. If we are in a simulation, then the reason we don't see aliens might be breathtakingly simple. The simulation doesn't include them. Why would it? If someone is simulating the history of a single civilization on a single planet, they don't need to populate the entire galaxy with other civilizations. That would be a waste of computational resources. You'd simulate the stars, sure. You'd need the night sky to look right. You'd need the physics to be consistent. But you wouldn't bother putting actual living beings on planets that your simulated subjects will never visit. The silence of the cosmos might not be a mystery at all. It might just be an optimization choice by whoever is running the program. This is the point where most people either find the idea thrilling or deeply disturbing, and honestly, both reactions are completely reasonable. The simulation argument doesn't give you comfort. It doesn't resolve the Fermi paradox so much as dissolve it. It says the question might not even be meaningful because the premises might not be real. But let's step back for a moment, because I think it's worth noting something about all 3 of these ideas: the zoo hypothesis, the planetarium hypothesis, and the simulation argument. They share a common feature, and it's one that makes many scientists uncomfortable. they're all essentially unfalsifiable, or at least extremely difficult to test. The zoo hypothesis says they're hiding. The planetarium hypothesis says our observations are manufactured. The simulation argument says reality itself might be artificial. In each case, the absence of evidence is reinterpreted as evidence of the explanation. And while that doesn't make them wrong, absence of evidence is not evidence of absence, as the saying goes. It does put them in a strange epistemological category. They're more like philosophical positions than scientific hypotheses. You can argue for or against them, but you can't really test them. Not yet, anyway. Some physicists have actually tried to think about what tests might look like. In 2012, Silas Bean and colleagues at the University of Washington published a paper suggesting that if we're in a simulation running on a discrete lattice, a grid of points rather than continuous space, there might be subtle signatures in the energy spectrum of ultra-high energy cosmic rays. The idea is that the lattice structure would impose a preferred direction in space, a kind of cosmic grain, like the weave of a fabric. And you might be able to detect it. It's speculative, and the results so far haven't shown anything conclusive, but the fact that serious physicists are even asking the question tells you something about where the conversation has gone. And that conversation has gone somewhere that Enrico Fermi, sitting at that lunch table in Los Alamos in 1950, could never have imagined. He asked a simple question: where is everybody? And 70+ years later, the attempt to answer it has led us from radio telescopes to evolutionary biology to thermodynamics to philosophy of mind to the fundamental nature of reality. The question has become a lens through which we examine everything we think we know about the universe and our place in it. But there's one more dimension to the Fermi Paradox that we haven't really talked about yet, and it might be the most practically important one. It's not about where the aliens are. It's about what the answer means for us, for our future, for our choices, for the kind of civilization we're trying to become. Because depending on which explanation turns out to be correct, the implications for humanity's long-term survival are radically different. And that's worth sitting with for a moment. Think about it this way. If the reason we don't see anyone out there is that intelligent life is just extraordinarily rare, if the great filter is behind us, if the hard steps were things like abiogenesis, or the leap to eukaryotic complexity, or the emergence of language and abstract thought, then we're in an incredibly privileged position. We made it through. We're on the other side of the bottleneck, and the universe, in a sense, is ours for the taking. Not in some aggressive colonial way, but in the sense that there's no one else out there to bump into, no competition for resources on a cosmic scale, no older civilization that's going to show up and tell us what to do. The galaxy is quiet because we're among the first, maybe the first, to get this far. And if that's true, then the responsibility that comes with it is staggering. Because everything we do from here on out matters not just for us, but potentially for the entire future of intelligence in this region of the cosmos. Now, contrast that with the alternative. If the great filter is ahead of us, if civilizations regularly get to roughly our level of technology and then destroy themselves, or stagnate, or collapse, then the silence of the universe is a warning. It's the most important warning we could ever receive, and we're receiving it right now. Every time we point a radio telescope at the sky and hear nothing, the silence itself is the message. And the message is, almost nobody makes it past this point. This framing was articulated most clearly by Nick Bostrom, the same philosopher who gave us the simulation argument. In a 2008 essay, he made a point that sounds counterintuitive at first, but becomes deeply logical once you think it through. He said that we should hope, genuinely hope, that the search for life on Mars comes up empty, that finding even simple microbial life on Mars would be terrible news for humanity. And here's why. If life arose independently on both Earth and Mars, that tells you abiogenesis is easy. It's not a hard step. It's not a significant filter, which means the filter, the thing that explains the silence, must be somewhere else, somewhere ahead of us. Every time we discover that one of the early steps is easy, it pushes the filter forward in time, closer to our present, closer to our future. And that means the thing that kills civilizations is still coming. We haven't passed it yet. So paradoxically, the more we discover about how common the ingredients for life are, and remember, we've been finding those ingredients everywhere. Amino acids on meteorites, water on moons of Jupiter and Saturn, organic molecules in interstellar gas clouds, the more nervous we should be. Because all of that evidence suggests the early steps aren't the filter. And if the early steps aren't the filter, then what is? This is where the Fermi Paradox stops being an abstract puzzle and starts being a practical framework for thinking about existential risk. And that's a term, existential risk, that has become a serious field of study in the last couple of decades, largely driven by people who take the logic of the paradox seriously. Organizations like the Future of Humanity Institute at Oxford, which Bostrom founded, or the Center for the Study of Existential Risk at Cambridge, which was co-founded by Martin Rees, the Astronomer Royal. These institutions exist in part because their founders looked at the Fermi Paradox and thought, we need to take this seriously. The silence of the cosmos might be telling us something about the fragility of technological civilizations, and we should probably figure out what that something is before it's too late. So what are the candidate filters that might still be ahead of us? We touched on some of these earlier: nuclear war, engineered pandemics, runaway artificial intelligence, ecological collapse. But let's think about them now not as abstract possibilities, but as specific, concrete risks that real people are trying to quantify and mitigate. Take nuclear weapons first, since that's where the story started, in a sense. Fermi himself worked on the Manhattan Project, and the lunch conversation in 1950 happened at Los Alamos, the birthplace of the atomic bomb. We talked earlier about Vasily Arkhipov and Stanislav Petrov, those moments when the world came within a hair's breadth of nuclear war. But here's what's sobering. Those are just the incidents we know about. Declassified documents have revealed dozens of close calls, broken arrows, false alarms, miscommunications that the public didn't learn about until years or decades later. In 1961, a B-52 broke apart over Goldsboro, North Carolina, and dropped 2 hydrogen bombs. One of them went through several stages of its arming sequence. A single low-voltage switch, one switch, prevented a 4-megaton detonation over the American East Coast. The engineer who later analyzed the weapon, Parker Jones, wrote in a now declassified report that one simple dynamo technology low-voltage switch stood between the United States and a major catastrophe. One switch. And nuclear weapons are, in a sense, a known risk. We've lived with them for 80 years. We've developed some institutional safeguards, some treaties, some norms. They're terrifying, but they're familiar. The risks that keep existential risk researchers up at night are the ones that are newer, less understood, and potentially harder to control. Engineered pathogens, for instance. The tools of synthetic biology have become dramatically more accessible in the last 20 years. What once required a state-level bioweapons program can increasingly be done with commercially available equipment and publicly accessible genetic sequences. In 2018, Canadian researchers at the University of Alberta synthesized horsepox, a close relative of smallpox, from scratch using mail-ordered DNA fragments for about $100,000. They did it for legitimate research purposes, but the demonstration made a point that was hard to ignore. The barriers to creating dangerous pathogens are falling, and they're falling fast. A natural pandemic like COVID-19 killed millions and disrupted global civilization for years. An engineered pathogen designed for maximum transmissibility and lethality could be incomparably worse. And unlike nuclear weapons, which require massive industrial infrastructure, bioweapons could potentially be developed by small groups or even individuals. Then there's artificial intelligence, which has moved from science fiction to front-page news in just the last few years. The concern here isn't the Hollywood scenario of robots deciding to exterminate humanity, though some serious researchers don't entirely rule that out. The deeper concern is about alignment. If you build a system that's significantly more intelligent than any human, how do you ensure that its goals, its optimization targets, to use the technical language, remain aligned with human values and human flourishing? This is what Stuart Russell at Berkeley calls the alignment problem. And it's genuinely hard. Not hard in the way that building a faster chip is hard, where you basically know what you're trying to do and just need better engineering. Hard in a fundamental, possibly philosophical way. Because specifying what we actually want, what human values actually are, in all their complexity and contradiction, turns out to be an incredibly difficult thing to formalize. And a super-intelligent system that's optimizing for the wrong objective, even slightly wrong, could be catastrophic in ways that are hard to predict or control. Here's the thing that connects all of these risks back to the Fermi Paradox. Every one of them is a plausible filter. Every one of them is something that could, in principle, explain why technological civilizations don't last long enough to colonize the galaxy, or even to make their presence known across interstellar distances. And the fact that we're facing all of them simultaneously, nuclear weapons and biotech and AI and climate disruption and resource depletion, suggests that maybe the filter isn't any single catastrophe. Maybe it's the gauntlet. Maybe every civilization that reaches our level of capability has to run a gauntlet of self-created existential risks, and the odds of getting through all of them over centuries and millennia are just very low. This is sometimes called the narrow window argument, and it has a certain grim elegance to it. The same intelligence that lets a species develop technology also lets it develop weapons. The same curiosity that drives scientific discovery also drives the creation of things that can destroy you. It's not that civilizations are stupid or careless. It's that the transition from a planet-bound species to a spacefaring one requires passing through a period where your destructive capability outpaces your wisdom, your institutions, your ability to coordinate and restrain yourselves. And maybe most civilizations don't make it through that window. But, and this is important, maybe some do. That's the hopeful reading. If even a tiny fraction of civilizations navigate the gauntlet successfully, then the galaxy should eventually be full of them. Which brings us back to the paradox. Unless the gauntlet is essentially impassable, the filter ahead hypothesis still has to explain why we see nobody at all. And that's where the math gets uncomfortable again, because even a very high failure rate, say 99.9%, still leaves thousands of surviving civilizations in a galaxy with hundreds of billions of stars. You'd need the failure rate to be essentially total, or you'd need to combine it with other factors: vast distances, different communication methods, deliberate hiding, to explain the silence. So maybe the answer isn't any single explanation. Maybe it's a combination. Maybe life is somewhat rare, and complex life is rarer still, and intelligent life is rarer yet, and technological civilizations face a brutal gauntlet of existential risks, and the ones that survive are separated by such enormous distances that they simply haven't found each other yet. Stack enough partial filters together, and you can get to silence without needing any single one of them to be absolute. This is sometimes called the many filters or compound filter approach, and honestly, it might be the most realistic framework we have. It's less dramatic than a single great filter, less tidy, but it matches what we actually observe. A universe that seems to have all the ingredients for life, that seems like it should be teeming, but that remains, as far as we can tell, profoundly quiet. And this compound view has a practical implication that matters enormously. Because if the filter is distributed, if it's many small hurdles rather than one big wall, then every hurdle we clear improves our odds. Every existential risk we successfully manage, every century we survive without destroying ourselves, tips the balance a little more in our favor. It means our choices matter. It means the decisions we make about nuclear arsenals and biosecurity and AI governance and climate policy aren't just political questions or economic questions. They're questions about whether our species joins the ranks of civilizations that made it through or becomes another data point in the silence. And that brings us to something that a growing number of thinkers have started to articulate. The idea that the Fermi Paradox isn't just a question about aliens, it's a mirror. It reflects back at us everything we are and everything we might become. The astronomer Carl Sagan understood this instinctively. He spent much of his career arguing that the search for extraterrestrial intelligence was inseparable from the question of our own survival. If civilizations tend to destroy themselves shortly after developing radio technology, he said, then SETI is likely to fail, not because intelligence is rare, but because it's fleeting. And if SETI succeeds, if we do detect a signal from a civilization that's been around for millions of years, then that's the most hopeful possible news, because it means long-term survival is achievable. It means someone figured it out. There's a concept in SETI circles called L. It's the last variable in Drake's equation, the one we haven't really lingered on yet. L stands for the average lifetime of a communicating civilization. And of all the variables in Drake's equation, L might be the most important, because it dominates everything else. If L is short, a few hundred years, say, then even if civilizations arise frequently, there are very few of them at any given time, and the chances of two existing simultaneously within communication range are vanishingly small. But if L is long, millions of years, tens of millions, then the galaxy could be full of ancient, enduring civilizations, and the question becomes not whether they exist, but why we haven't heard from them. And here's what's fascinating about L. It's the one variable in the Drake equation that we have some control over. We can't change how many stars form, or how many have planets, or how often life arises. but we can influence how long our civilization lasts. Every decision we make about how to handle the risks we face is, in a very real sense, a contribution to the value of L. And that's what makes the Fermi Paradox so much more than an academic puzzle. It's a mirror. It takes this enormous cosmic question, where is everybody, and turns it back on us and says, the answer might depend on what you do next. Think about that for a second. You started this journey lying here in the dark, listening to a story about a physicist cracking a joke at lunch in 1950. And now we've arrived at a place where the silence of the universe is asking something of us. That's a remarkable arc, if you think about it. Enrico Fermi tossed off a question between bites of his sandwich, and 70-some years later, the deepest version of that question is essentially, can a technological civilization grow up fast enough to survive its own power? And L, that variable, the longevity of a communicating civilization, it sits there at the end of Drake's equation like a final exam. Everything else in the equation is prologue. Stars form, planets coalesce, chemistry becomes biology, biology becomes complexity, complexity becomes intelligence, intelligence builds radios and rockets. And then what? That's L. That's the part of the story we're living in right now, the part that hasn't been written yet. Frank Drake himself was always cautiously optimistic about L. He tended to estimate it in the thousands to tens of thousands of years, which, if you pair it with even modest estimates for the other variables, gives you a galaxy with a reasonable number of civilizations in it at any given time. But Drake was careful to point out that his optimism wasn't based on evidence. It was based on hope, and on the belief that intelligence, once it reaches a certain level of self-awareness, tends to choose survival. That's a beautiful thought. It's also, as Drake would have been the first to admit, completely unproven. Other estimates of L are much grimmer. If you take the compound filter idea seriously, that civilizations face not one existential gauntlet, but several overlapping ones, nuclear weapons and engineered pathogens and artificial intelligence and climate disruption, and things we probably haven't even thought of yet, then L might be disturbingly short. A few centuries, maybe less. In that case, the galaxy could be littered with the ruins of civilizations that flared briefly and went dark, like sparks from a fire that never quite caught. And we wouldn't know, because those sparks burned out long before their signals could reach us, or because their signals are washing over us right now as faint, indecipherable whispers buried in the noise. But here's the thing about L that I find genuinely moving, and it's the reason I wanted to save it for last. L is not a fixed number. It's not like the mass of a proton or the speed of light. It's not a constant of nature that we discover and write down. L is a variable that we create. Every generation contributes to it. Every institution we build, every treaty we sign, every safety protocol we implement, every moment where someone like Stanislav Petrov decides not to push the button, all of that is L being written in real time. And every war we start, every ecosystem we collapse, every dangerous technology we deploy without adequate safeguards, that's L being shortened. There's a lovely thought experiment that the astronomer Seth Shostak likes to pose. Imagine you could somehow listen in on every civilization that has ever arisen in the Milky Way. What would you hear? If L is typically short, you'd hear a cacophony of brief transmissions, bursts of radio noise lasting a century or two, scattered across billions of years, almost none of them overlapping. It would be like standing in a dark field the size of a continent, with fireflies blinking on and off at random, each one glowing for just a fraction of a second. The chances of two fireflies being lit at the same time, close enough to see each other, vanishingly small. But if L is long, if even a small fraction of civilizations figure out how to persist for millions of years, then the field would be dotted with steady, enduring lights. Beacons. And those beacons would be detectable, because they'd have had time to build powerful transmitters, or to spread across multiple star systems, or to engineer things on a scale that we could spot with our telescopes. The fact that we don't see those beacons, that's the Fermi Paradox in its starkest form, and it's why L matters so much. If long-lived civilizations are common, we should see them. We don't. So either they're not common, or they're hiding, or they're there and we're not looking right, or, and this is the possibility that keeps the existential risk researchers up at night, maybe L just isn't very long for anybody. But I don't want to leave you with dread, because that's not actually where the best thinkers on this subject end up. The people who think most carefully about existential risk, people like Toby Ord at Oxford, who wrote a book called The Precipice about exactly this, they tend to arrive at a position that's neither naive optimism nor fatalism. Ord estimated that humanity faces roughly a 1 in 6 chance of existential catastrophe in the next 100 years. That's sobering. That's Russian roulette odds. But it also means there's a 5 in 6 chance we make it through. And if we make it through the next century, if we navigate the transition from a civilization that can destroy itself to one that has chosen not to, then the future opens up in ways that are almost incomprehensible. Ord calls this period we're living in the precipice, a narrow, dangerous ledge between the development of world-ending technologies and the development of the wisdom and institutions needed to manage them. And his argument is that we are, right now, at the most critical moment in our species' entire history. Not the most dangerous moment in terms of any single threat, necessarily, but the most dangerous in terms of the sheer number and variety of threats converging simultaneously. We've been around for roughly 300,000 years as a species. We've had nuclear weapons for less than 80. We've had the ability to engineer pathogens for less than 20. We've had powerful artificial intelligence for, well, depending on how you measure it, maybe 5 or 10 years. The pace of capability is accelerating, and the pace of wisdom isn't keeping up. And this is where the Fermi Paradox becomes not just a scientific question, but something almost philosophical. Because if Ord is right, if we really are on a precipice, then the silence of the cosmos is telling us something important about the nature of that precipice. It's telling us that it's hard to cross. Maybe not impossible. We can't know that from silence alone, but hard. Hard enough that the galaxy isn't obviously teeming with ancient super-civilizations. Hard enough that whatever the great filter is, or whatever combination of filters there are, the net effect is a cosmos that looks, from where we stand, very quiet. And yet, we're still here, we're still listening. Jill Tarter is still advocating for expanded SETI searches. The James Webb Space Telescope is analyzing the atmospheres of exoplanets, looking for biosignatures, oxygen, methane, the chemical fingerprints of life. New radio telescopes are coming online with sensitivities that would have seemed like science fiction a generation ago. The Breakthrough Listen project, funded by Yuri Milner, is conducting the most comprehensive SETI survey ever attempted, scanning millions of stars across a wide range of frequencies. We are, right now, in the early stages of what might be the most profound search in human history, and we've barely started. Jason Wright, remember him? The Penn State astronomer who pointed out how little of the cosmic haystack we've actually searched. He likes to say that declaring the search a failure at this point is like dipping a glass in the ocean, finding no fish in it, and concluding the ocean is empty. We've searched a tiny, tiny fraction of the possibilities, the frequencies, the directions, the types of signals, the timescales. The parameter space is so vast that our efforts so far, heroic as they've been, amount to almost nothing. That's not discouraging. That's actually exciting. It means the question is still wide open. It means every new telescope, every new detection algorithm, every new idea about what to look for, any one of those could change everything. And maybe that's the right note to settle into as you lie here in the dark, letting all of this wash over you. The Fermi Paradox doesn't have an answer. Not yet. Maybe not ever, at least not a definitive one. But it has something better than an answer. It has a question so deep and so fertile that it touches everything. It touches biology and physics and chemistry and philosophy and politics and ethics. It asks us who we are, whether we're alone, whether intelligence is a cosmic commonplace or a freakish accident, whether the universe is full of life, or whether this one pale blue dot is it. The whole show. The only place where anyone has ever looked up at the stars and wondered. You know, there's a passage from Carl Sagan. And I keep coming back to Sagan because he understood better than almost anyone how to hold the scientific and the human sides of this question together. There's a passage where he talks about the Earth as seen from a great distance. He was describing the famous pale blue dot photograph taken by Voyager 1 in 1990 from about 6 billion kilometers away. In that image, Earth is less than a pixel, a tiny, faint speck suspended in a sunbeam. And Sagan wrote that everyone you've ever heard of, every human being who ever lived out their lives on that mote of dust. Every act of kindness, every war, every invention, every love story, every moment of genius and every moment of foolishness, all of it, on that barely visible point of light. And when you hold that image in your mind and then think about the Fermi Paradox, something shifts. The question stops being abstract. It becomes intimate. Because if we are alone, if the great filter is behind us and we really are the only ones, then that tiny dot is unspeakably precious. It's the only place in the entire observable universe where anyone is asking these questions, telling these stories, building these things. And if we're not alone, if there are others out there, separated from us by vast gulfs of space and time, then the dot is still precious, but in a different way. It's precious because it's ours. It's the place where we get to contribute our own small chapter to whatever larger story the universe is telling. Either way, the silence means something. Either way, it matters what we do with the time we have. So as you drift off tonight, let the paradox just sit with you. You don't need to solve it. Nobody has. Some of the smartest people who have ever lived have spent their careers circling around it, and the best they've been able to do is narrow the possibilities, rule out a few things, and stand in honest wonder at how much we still don't know. And that's okay. That's more than okay. That's the whole point of science, not to arrive at certainty, but to ask better and better questions, to refine our ignorance into something precise and beautiful. The stars are still out there. The radio telescopes are still listening. Somewhere, right now, a graduate student is writing code to sift through terabytes of data from the Breakthrough Listen project, looking for a pattern that doesn't belong to any natural source. Somewhere, a planetary scientist is studying the latest spectra from an exoplanet atmosphere checking for combinations of gases that shouldn't coexist unless something is producing them. Somewhere, a philosopher is writing a paper about what it would mean for our understanding of consciousness if we discovered that intelligence arises inevitably wherever conditions allow. The search goes on. It goes on while you sleep, while you dream, while the earth turns and the stars wheel overhead in their ancient, patient arcs. And maybe tomorrow, or next year, or in 100 years, someone will find something. A signal, a biosignature, an artifact, something that changes the answer to Fermi's question forever. Or maybe they won't, and the silence will deepen, and that will be its own kind of profound knowledge. The knowledge that we are, against all odds, something rare and extraordinary in a universe that didn't have to make us at all. But for now, tonight, just let it be a question. Let it be the best question anyone has ever asked. Where is everybody? And let the quiet of the night be its own kind of answer. Not an empty quiet, but a full one, rich with possibility, heavy with stars you can't see, alive with the hum of a universe that is still, after 14 billion years, full of surprises. Rest easy. The cosmos will keep its secrets a little longer. And you're part of the story, whether you're awake for it or not.